So I'll be talking about the concept of operation and smart requirements. For concept of operation, I'll be talking about how we came up with our project and also the operation of our project after it launches into space. We came up with our project when we thought climate change is a big topic right now, and one part of it is the ice melting. And we thought, what are the other things that happens when ice melts other than sea level rising? And we found out that fresh water decreases solubility of ocean salt water, which slows down the ocean circulation. And ocean circulation is a key regulator of climate by storing and transporting heat, carbon dioxide, and fresh water around the world. It also regulates the weather and its magnitude, and jar helps with circulation, which is the big part of ocean circulation currently for this project. It is a large system of circulating ocean currents and also helps form garbage patches. Some of our questions when we research about it is if the circulation of the ocean slows down, what will happen to the garbage patches? Will it flow in its original position, or will it move around the ocean and reach the shores of densely populated areas? Some of the potential effects we listed for movement of plastic and garbage dumps in the ocean are microplastic entering our food source and body, predict where the garbage will end up in the ocean. Ocean circulation is lumping all garbage into one specific area, and if the circulation stops, garbage will be freely moving and more spread out. And this can prevent the absorption of CO2 by the ocean. Our operation when the satellite launches is every 2 weeks. The first satellite or the first cube, because we're using 2U, um, it will be taking pictures of garbage patches near populated areas and cloud pictures and evaporation of water to determine the current circulation. Um, and then all the data are gathered and processed by the second cube, which also collaborates with a larger satellite that tracks salinity of the ocean, because salinity is too big for cubes um physical physical space. It then relay all those data to the ground station, and all data from that satellite will be analyzed at the ground station. As for the smart requirements, I'll be talking about the smart and flowing down requirements of the project. For us, we have it reading images to the MIT ground station, and those gathered data or images will be wind circulations using the cloud movement and the radiometer, salinity by microwave emissivity from a bigger satellite, trash circulation, which we get from pictures from populated cities near coasts like San Francisco and New York. For M, measurable, we're thinking of having 5 years of operation at least, because fully gathering data for the project will take a long time. A, attainable, our next goal currently is fully functional Raspberry Pi for our cubes. Our relevant is it will be operating at the LEO orbit and connected to a bigger satellite for, again, the salinity data we need for our research. The T time bound is that data gathering is once or twice a month because of the slowness of currents or changes of water solubility because of fresh water melting or ice melting. For flowing down requirements, we are thinking of making 2U CubeSat. The z-axis real max distance would be 227 millimeters and max mass would be 3.6 kilograms. The first cube job is to take data, more specifically ocean and trash circulation, except for salinity, because again, it's too small for salinity data gathering. Second cube would be data gathering from that big satellite light that's gonna give us that salinity data, and also the first cube, which is the ocean and trash circulation. Um, some parts, half of the second cube will also be part of the first cube because of the radiometer being 1.5 U. And this is our resources.
Hello and welcome to a brief overview of the AstraNavis CubeSat satellite. Here I will be going over our brief structural design. As of now, we have designed the 5 outermost panels and the internal mounting systems. As you can see, these panels will be made out of aluminum as shown in this part's highlight, and the internal assembly brackets will also be made out of aluminum, and we've elected to go with a lower profile on the brackets with the trade-off of having more to maximize the space we have to mount things internally. And we've, as far as internal mods go and parts, we currently are still finalizing what we would like to see inside of the satellite, though as of now we will add to the CAD soon a Raspberry Pi 4 for command and data handling, a power distribution box for, obviously, power distribution, an Adafruit non-DLF IMU to handle acceleration, gyroscopic, and dispositional data, as well as a UHF radio from Alpha Wolf, and a radiometer and mantis imager for the CubeSat to carry out its mission. And yes, that concludes the tour. Thank you.
Hello, this is Ethan Ponce, and I'm here to talk about the mass and data budget. For the data budget, we want to use JPG type files, as we are mainly using photographic images that would be used to recognize patterns in ocean circulation, making JPG an ideal image type. We also want to utilize radio waves for sending and receiving information, with us specifically using a UHF or VHF radio. Here we can see the downlink and uplink frequency of said radio, as well as more specifications for the type of image we will be using. Now we'll move on to the mass budget. When it comes to the list of supplies, we will mainly be using the supplies given to us for the CubeSat course, as well as a few additional items. Overall, the cost comes to $228.51. The total mass of the CubeSat with these items comes to about 0.444 kilograms, give or take an additional range of plus or minus 0.1 kilogram to that.
Hello, my name is Christian. I'll be going over our team's CubeSat block diagram. Within our CubeSat block diagram, it includes a power subsystem, which includes 4 body-mounted solar panels, a power distribution box, and batteries. We also have the structured subsystem, which includes the deployable solar panels and an aluminum chassis. Connected to the power distribution box, we have the command and data handling subsystem, which includes our Raspberry Pi 4. Connected next is our altitude, determination, and control subsystem, which includes our Adafruit 9DOF IMU. We also have a telecom, which includes a radio, a thermal subsystem, which includes the heaters, and our payload, which includes our radiometer and mantis imager. In our flowchart, as you can see, is followed in this order of a structure integration to electrical harness integration, then power electronics, Then we will install our battery and also integrate our thermal components. Followed that, we would have a CDHS test and solar panel integration and testing. After, we will have a pre-environmental test and have testing of our heaters. Next, we will install our radios and then test them, and then install our ADCS and test them afterwards too. Next, we will actually install our payload, and with that, we will start testing our radio meter and Mantis imager. Then follow would have a vibration test and have a electrical connection check just to make sure that all connections are still intact. Then we will collect wind circulation data and transmit our test data from our CubeSat to an actual radio station where we could analyze the data for ocean circulation and have an accuracy check. Once we see that everything's working, we will prepare for launch.
And this is our power budget for our CubeSat. As you can see from the left, our command and data handling will be using our Raspberry Pi 4. Before that, all our power usage is it's about estimates because they were quite hard to find the actual power usage of each component. So these are rough estimates with contingency of relatively high. So with Raspberry, we have about 5.5, contingency of 20, which gives out total mature power of 5.78. While EPS, about 12.45, contingency about 20, which leaves us with 30.07. Our attitude determination will be our IMU, about 0.06 watts, with contingency of 5, which leaves us about 0.07 watts. Our telecom will be using a radio, 3.8 with contingency about 20. That gives us roughly about 4 mature power of 4. And then our instruments with the payload will be using a radio meter with nominal unit of 1.5, contingency of 10, which gives us a mature power of 1.65, and a Mantis imager, the camera, which will give us a unit power of 2.5, contingency of 5, and a total mature power of 3. And then our CubeSat will have two modes, a science mode and downlink mode. The only really difference between these two is that during science mode, everything is on, while in downlink, the payload is off. All of the payload will be off.
Okay, so on to link budget. We have specified a radio, and by the specifications provided by the manufacturers, the uplink is at a frequency of 146 megahertz. The downlink is at a 438 megahertz. First, we need to calculate our EIRP. It's the radiated power, basically how much is being like pushed in towards the ground station. We can find that by adding the power of transmission plus the gain. We want it to be in decibels, so we use the conversion of 10 times the log of our power. And since the the gain for our radio is 0, we just end up with the value of 4.9136 decibels watts. Then we want to find free space loss, which is how much energy is lost due to it just traveling through the atmosphere, and yeah. And we also want that in decibels, so we use a conversion of 10 log, but the actual value that we convert is 4 pi times 160 times 10 to the third times 438 times 10 to the sixth divided by the speed of light squared. Speed of light is defined as c as 299,792,458 meters per second. And basically, calculating that, we end up with a decibel value of 129.3597 decibels. Then we calculate the power received by the ground station, which is just the EIRP minus the FSLR plus the gain. There's a slight mistake there, but it should be the EIRP minus the FSL, but since also plus the gain of the receiver, it needs to have a plus 45.8. And so basically, if we add 61 plus 45.8. The actual power received should be negative 78.6461. And then we can just find the noise by using the formula of Boltzmann constant times the frequency times the not the frequency, the bandwidth times the temperature of the system. And we can also use the conversion to get a decibel of negative 132.3687. We can now find the signal to noise ratio. However, since my power receive was incorrect there, I'll be using the right one right now. So if we get negative 78.6461 as our power received, and then we minus out the negative 132.3687, we actually end up with a SNR value of 53.7226, which is a lot closer to our downlink, our uplink value. So that makes a lot more sense. But yep. We do want a link margin of like 1 decibel for our general purpose use. It doesn't really need to be much higher. And for that, we need a wattage of 3.9, as you can see at the top. However, our power budget is about 3.8, but that still should be fine. We can still make a link margin of about 1, especially since we don't need it to be accurate to the point where it needs to be up to 3 decibels. And now calculating uplink, it's basically the same thing. We end up with this is from the ground station to the satellite. Our EIRP is about 61.5978 decibels. Our FSL is with the after converting is 119.8172. And then our PR is just the EIRP minus the FSL, which is a 61, which is our EIRP minus 119. And since the gain received is 0 because of our radio specifications, which were given, and it has a gain of 0, we get a negative value of 58.2194 decibel watts. And we can find the noise by the same formula, plug in the converter, and we get negative 130.1536. And then our signal to noise ratio is 71.9342 decibels. And we don't really need to worry about the link margin here because the wattage can be adjusted to be much higher on the ground station because it is on the ground, and whenever is needed, the antenna can send out more power if required. But overall, for the one correction, the SNR needing to be 53.7226 for our downlink, and our uplink thing of 71.9342 should be fine. Considering this is a cube satellite communicating with ground stations, the SNR is a very nice value. And yeah,